Good afternoon, everybody, and welcome to this next session of the DSP online conference, which is titled Building a Tensorflow Lite Neural Network Vibration Classifier with a little help from digital signal processing. My name's John Edwards. As some of you guys know me from previous talks, for our colleagues in the US, I'm not the John Edwards you see on the left. There won't be any extramarital affairs or scandals in this talk. I'm actually a DSP and machine learning embedded systems consultant with around 40 years of experience in the digital signal processing field. I started in V-series modems in the early 1980s, worked through mobile phone networks, audio signal processing, and now I'm working in machine learning applications specifically for vibration analysis. I'm the author of the SIGLibe DSP machine learning library, which is on GitHub at the URL shown. I'm also the course director of the digital signal processing course at the University of Oxford and regular presenter at conferences. Here's a high-level agenda for today's talk. We're going to have introduction to vibration analysis, overview of the neural network, and then we're going to get into the heart of the talk, which is the code walkthrough, the Python code. I'll finally finish with some hardware implementation notes and then a quick summary. Okay, so to introduce the talk to start with, we're going to walk through a Python notebook that uses a combination of digital signal processing and a convolutional neural network to classify multiple vibration modes of a rotating machine using time series classification. The key to developing this code to run efficiently on an embedded processor is the use of the DSP algorithms to optimize the task of feature extraction. So we're basically going to simplify the features that the neural network can then classify. The DSP code will be used to pre-process the data, which will then be passed to a TensorFlow model, and we'll develop the TensorFlow model, we'll run the code, and ultimately we will develop a TensorFlow Lite model, which we will then test to ensure that fixed point model works as well as the floating point model, hopefully. Okay, so quick introduction to vibration analysis, and this first section is really quick because the key of the talk is the code run through. We can analyze signals in either the time or frequency domain, and the vibration signals that we're using in this tutorial are shown here. I've got a time domain frame on time domain frames on the left of two different signals and the frequency content on the right. We can see, as humans, that the time domain sequences are different, but if we had lots of different sequences that were very similar, it would be very difficult to tell them apart. However, when we look at the frequency domain, the spectra of those signals, we can much more easily see the differences in those signals. And indeed, it is those differences that we're going to, or those signals that we're going to pass to the neural network, and the neural network's going to classify the frequency domain signals rather than the time domain signals. To show you those graphs in slightly different format, these are spectrogram plots of the same two sequences and again, these are highlighting the differences between the two signals. And you can see in the bottom one, there is a very distinct harmonic at 5 kilohertz, which is not quite so prevalent in the top motor spectrogram. And it's those differences that we're going to see that the neural network is going to be very easy to detect. Okay, so that's a very high level view of what we're going to do. There'll be more detail in a minute. Let's look at the neural network and what I like to call intelligent AI, because the key to all of this is the feature extraction that we are going to apply to the signal prior to applying those signals to the neural network for classification. So here's a very high level diagram of what we are going to be doing. We have an AI model that we can deploy on different systems, and we need to pre-process that data for both training the neural network, the model, and when we come to predicting the classes of, in this case, vibration that we are going to be looking at. There are many, many different ways that we can perform that pre-processing feature extraction process. In the speech world, Kepstrom analysis is a very common example. We could do some very simple feature extraction operations such as peak detection, zero crossing, etc., etc. But for this talk, we're going to discuss spectrum analysis, the fast Fourier transform. And there's a reason for that I've found in vibration analysis, that the Kepstrom gives you a logarithmic frequency spectrum, which is much more suitable to speech analysis, whereas for vibration analysis, a traditional fast Fourier transform with a linear frequency spectra gives much higher performance. Okay, so you could say, and going back to our earlier slides, you could say, well, okay, let's use the big data approach to this problem. Let's just chuck lots of time domain data at the neural network and let the neural network do the work for us. Why are we putting all this effort in to develop the pre-processing, the feature extraction, the fast Fourier transforms, when actually we could just let the neural network do the work for us and we can go and have a coffee? Well, when I was first researching this project several years ago now, I was looking around at different options, and one of the things I looked at was, can we get a neural network to implement an FFT? And fortunately, somebody, his name's Endelith, or his GitHub name is Endelith. I have no idea who he is, but he solved this problem for me, or solved the question for me. And you can see his code on his GitHub gist. And basically, the summary of his work is that, yes, you can get a neural network to implement your DSP algorithm, but unfortunately, it requires an awful lot more MIPS and memory to do the same process that we could perform with a fast Fourier transform. So if we're going to try and reduce the MIPS, the memory, the cost, power consumption, all of these cost features of our system, then we need to implement those DSP algorithms using traditional approaches rather than just the big data approach. So this is why I like to call it intelligent AI. We are applying some intelligence and thought to the process of feature extraction ahead of applying the neural network, so that we can reduce the overall cost, whatever that cost is, of our system. Okay, so here's a high-level view of the application, particularly focusing on the DSP code. The key four modules that we're going to perform are shown in grey. There's the Blackman window, the fast Fourier transform, and then the magnitude extraction and the logarithmic dB scaling. You can see mentioned on there is a number of cores and a power quad. My first implementation of this, which I'll talk about at the end, was actually on an NXP power quad device. I'll talk about that at the end. Okay, so these are the main blocks of the system. I'm not going to focus on them now because I'll talk about them in more detail. Here is the very high level view of the network architecture. It's a very simple two trainable layer neural network. We have an input layer, hidden layer, and output layer where we can train the weights and the biases for the neural network, and we'll classify our signals. So we'll talk more about that when we look at the code. Finally, we'll be able to look at the results. Here is a graph of a 4-machine confusion matrix, the output results. Again, we'll see the outputs of this in the code. So without more ado, let us get on to look at the code. Excuse me a second while I just have a quick drink. Okay, let's get to the heart of the discussion, the code walkthrough. So here is the Python script. I hope you can see the text clearly on the screen. As the notes say at the top of the script, you can download the full source code for this. You could even follow along live if you like. You can claim the GitHub repo, and the Python code is in there. You can run it as I am running it. If you want a C++ version of this code, you can clone the DSP library repo as well, and you can run that as well. Okay, so let's just reconnect our runtime. So as I was saying, we're going the Python script. Last year, one of our colleagues, Matus Sejnek, and I apologise if my pronunciation of his name is wrong, gave a fabulous presentation where he basically worked through a live Python notebook, Jupyter Notebook, and wrote all his code and ran it, and it was great. I thought, wow, that's fabulous. I'm going to try and do the same, but with my vibration analysis code. So I started writing the code, like literally from a blank Jupyter Notebook, started writing the code, and after about an hour, I'd only got about halfway through. So I thought, Stefan's not going to like that. 2-hour talk is probably a bit too long. So I paused the recording, carried on writing the code, rewound, and so basically, rather than typing it all in live and taking 2 hours for the task, I'm going to talk through the code as we go and highlight all the important parts. Okay, so this is a Google Colab notebook, obviously, Jupyter Notebook. Sometimes we all need to work locally. We might not be online if I'm working with customer code or something like that. Then we might want to work offline, online, or a mixture of the two. So that is something I'm going to touch on very early on this during this talk. In terms of the Colab, Google Colab, we have various runtime options which we can see here. And we can change our runtime type to GPU, TPU, etc. In my experience, actually, for this type of work, and it's not true for all work, I've actually found that Colab is really not that much different to when I'm running the code locally on my laptop. So just a little pointer there. Okay, so what are we going to do? We're going to read in our data, our audio recordings from WAV files, and then we're going to perform the time series classification on those recordings. So before we read the files in, we need to import our relevant NumPy packages, Python packages, starting with NumPy, Tensorflow. So we're going to use Tensorflow and Keras in this project. I'm importing the OS package module for a bit of file handling and checking, which you'll see. Google Colab for importing files from a Google Drive, which is great. Working collaboratively, sharing data and scripts across Colab is a really, really great way of working if you're part of a team. You can all share the same data files, so you can import from your data files from Colab, as we're going to do here, and share everything about your project. We're going to use matplotlib for plotting some graphs. I use, there are various different ways of importing WAV files into a Jupyter Notebook. I tend to use the SciPy WAV file module, very good. And then we're also going to use scikit-learn for plotting some graphs. Okay, so top level configuration. All of these WAV files are 16 kilohertz, and we're going to use a frame size of 256 samples. Why did we choose that? Well, 256 samples equates to around 16 milliseconds. And actually the main reason for choosing 256 samples is to give us a large enough frequency domain resolution to separate out the frequencies of interest that we are looking for. So we are going to perform our fast Fourier transforms on our 256 input sample frames, but actually we only need to pass the frequency domain samples from the 0 Hertz to the Nyquist frequency onto the neural network. In other words, we only need the first half of that frequency domain frame to be passed to the neural network. So the number of input nodes on the neural network is equal to half the number of time domain input samples. So that's great. Immediately, using the fast Fourier transform, we've reduced the amount of data that we need to process in our neural network. Okay, so file I/O, I kind of mentioned that. Here is this section of code that checks if we are using Google Colab to read in the files from Google Drive, or if we are going to use a raw URL. And in this case, here's an example that you can use to download the same files from one of my GitHub repos. So we can we can run this code in Colab. It will grab the files off my Google Drive, or if I'm running the same code offline, it will in VS Code, for example, is my preferred work environment. Then it will just grab the same files from the GitHub or from any URL, to be honest. And then the next section just lists the WAV files that we are going to import. So it's a very easy way of configuring the system, because we can change the number of WAV files we're going to import, and if we write our Python code as for loops, it will import as many different waveforms as we want and classify as many classes. Okay, so there's the first two modules. Let's just run the first one. We will do our import. Then we will, hold on, read our files in. And there you go. Now, ordinarily, it would ask at this time if you want to connect to your Google Drive to load the code, and you click Allow. But I ran this code earlier on today, and so it was already authenticated on my Google Drive. So here we go. We've mounted the Google Drive location, and we've loaded the files. We've specified the files we're going to load, and we're only going to have two classes in this specific case. Now we could have more, and you could enable machines 3 and 4 and run those. It just takes a little bit more time, training, and so on. You'll get the same results as I showed in the presentation. So we're just going to stick with two machines, two classes at the moment, just to make things a little bit easier. Just a word a bit ahead of later on when we talk about the code. In terms of training, when you come to train your neural network, you can run a number of epochs on the data that you're processing, and the more epochs you run, the better your neural network trains, but clearly it takes longer. So if you guys try with more machines, more WAV files, you will need to increase the number of epochs to get good classification of the many different machines. In terms of numbers of machines, I've used this algorithm with slight changes to the DSP code for greater than 10 different machines and different vibration modes, so it's quite flexible. Just one final note about these recordings. These recordings were all made with a high quality industrial calibrated microphone. So a calibrated microphone with a very, very, very linear frequency response. Okay, so that's the file specified. Now we've got the section of code that is going to load the file. So for each file in the range of the number of classes, i.e. 2 classes, we're going to check to see if the files are already loaded, because if they are, we don't need to load them again. And if they're not, then we will go and grab them from whichever URL we've specified. We can either copy them, we can either get them if it's from a web URL, or we can just copy them to the local folder if it is on Google Drive, as we are now. But the files will be present. We then read in the WAV files, and this is one of the nice things about the SciPy WAV file functions. You can just read a file all in one go with wavefile.read, and then we're going to append that to our wave data, and we're going to print the results out. So here we go. Let's just have a look, and we're loading the files. There we go, and we can see that the first file is 3 million samples long, approximately 16 kilohertz. Second file is 2.8 million samples long, again 16 kilohertz. So again, with this little piece of code, this little bit of jiggery-pokery, we can run this code in VS Code, as I do, Colab, wherever we like. Actually, one aside on that sort of whole development environment options choice thing. Another thing that I find for this type of project, it's obviously developing in Colab or VS Code, running a Python notebook in VS Code. It is really powerful way to develop Python code, but it's not always the best way of deploying it to a development project environment, etc. So I would usually use Jupyter, the MB convert function, notebook convert, to convert to a regular Python script, which then can be automated in a shell script or wherever you like, in a Docker container, etc., etc. Okay, so we've loaded the data for our two classes. Let's just have a look at the data and see what it looks like. So our first little graph, it takes a few seconds for the data to be plotted, but hopefully, there we go. We can see the data. Okay, it's all bunched up. It's a very short little graph, but we can see the data for both of our machines. Okay, moving on to the next section. What we now need to do is to take these effectively 1D arrays of 1 million, 2 million, 3 million samples and convert these into 2D arrays that match the frame size that we need to process, which is our time domain frame length, which I discussed earlier. So our time domain frame length, 256 samples. So we're going to run this for loop, and basically it just loops around, taking each successive frame and adding it into a 2D array. So here we go, we have two 2D arrays for each waveform. We have the number of frames, so that's the number of 256 sample frames in each array, and you can see that the length of each frame is 256 samples. Okay, so now on to the DSP part of the task. So the DSP code, some of you may have used Tensorflow in the past, and you may have already seen that Tensorflow has a number of DSP functions, including the FFT. So you could say, well, why are you using NumPy, John? Why don't you just do everything in Tensorflow, use the tf.signal.fft function, and off you go? The reason is that NumPy gives much greater control and flexibility over the DSP functionality that we can use. So we can use many more functions, we can do lots of crazy things. And so this is much more useful in developing a real application. I found it was much easier to get my NumPy code to match what my C++ code was doing on an embedded DSP, so I could really, control that whole process, right from the quantizing the inputs on the front end. So if you want to simulate an A to D converter, you can simulate an 8-bit converter, for example, very easily in NumPy by just quantizing the data. So you can really build a whole model in NumPy of your whole signal processing chain as it will be implemented in a real system. And in fact, in a project I'm working on at the moment, we have a 10-bit A to D converter. So I'm just reading in my 16-bit samples from my stored wave files, quantizing them in NumPy, so that I know that the code is performing exactly as it would with the absolute real data. Okay, before I delve into the DSP functions in a little bit more detail, I did just want to say one thing about them. Excuse me a second. This is a very high level view. simple functions as I showed in the flow diagram. We're going to do some windowing, fast Fourier transform, and then we're going to aggregate the data for the neural network to process. In a real application where you maybe have many more classes of vibration that you want to detect or differentiate, categorize, you're going to need to do add a lot more functionality into this this part of the code to make it, you know, a robust deployable solution. But that's not really a that's probably a talk for maybe next year. Okay, so what we're going to do, we are going to pre-process. We're going to define a function that will pre-process our now 2D arrays. And in that function for pre-processing, we're going to perform our windowing function with the Blackman window. And why Blackman? You know, there are dozens of different windows that we can use. In my experience, the two main windows for this type of general purpose signal processing task are really the Blackman or the Hanning window. Some of you may know Blackman Harris, Fred Harris, talking here this week. Very useful for radar type applications, sonar and things like that. Fred will be able to tell you way more about that than I ever can. But for these type of applications, I find that the Blackman or the Hanning windows are perfectly adequate and very good separation of frequency and side lobe window magnitude. Okay, so we're going to do the window. We are going to create we're going to create an empty frame to store our FFT results in, and then we are going to process the data in our 2D array that is passed to this function. So we're going to multiply the input data by the window function. We are then going to pass the windowed result to the fast Fourier transform to get the FFT'd result. And then we're going to take the absolute value of that to get the magnitude out. And then we are going to truncate the output so that we are only, if you remember from the earlier part of the talk, we're going to only pass the first half of the frequency frame to the neural network, i.e. from 0 Hertz to the Nyquist frequency. So this is just extracting the first half of the frame. And then we're going to append that result to a new array, which we're going to call the FFT'd 2D array. And then we'll return that to our calling function. So that's the function defined and the process we're going to implement. We're going to create our FFT'd 2D array, empty set, and then we are going to append to that for every class. We are going to append the FFT'd 2D array for that class. So we take the input time domain data for that class, we pass it to the pre-process function here, we get the result of that, and we append it to our 2D array. So then we'll end up with a single 2D array with all of our data in. So let's go for that, hit run. This will take a few seconds, quite a bit of data. There we go. So we've got our if you like, class 1 2D array and our class 2 2D array. And now you can see that the arrays are of width, or the frame width is 128 samples. Perfect. Okay, so now we have our frequency domain frames. what we need to do is for the neural network, we need to split these frames into two. We need to use some of that data for training and validation and some for testing. Now, in practical applications, what I would do is use this data for training and validation, and I would use completely separate data from the machine for testing. But for the purposes of this talk, we're going to split the data into a training and validation set and a testing data set. So that's all we're really going to do here. We've got a function that's going to split into the training and test functions, because the training data set will then be used by Tensorflow to create the separate training and validation data sets. So at this stage, all we need to do is split these two arrays into our training stroke validation set and our testing set. So we'll do that, and there we go, very quick. So we have our class 0, and you can see we've split the original number of subframes, 11,810 frames into 10,629 and 1,181, and then we've done the same with our second class. We've split them 90 to 10%. Okay, so we've got our training stroke validation set and our test set. Now we need to convert these frames, which is still just a 2D NumPy array format, into a format that is suitable for TensorFlow. So basically, we have our separate arrays of our class 0 and our class 1 data, and we need to now create our TensorFlow training input and training output dataset. So that's the X train and the Y train, input and output, and the X test and the Y test, that's the input and output sequences. So we need to concatenate them, but at the same time, we also need to append the class number. So we need to tell TensorFlow that this part of the data in, for example, X train is class 0, this bit's class 1, this frame's class 0, this frame's class 1. So we need to append the class number to the data as well. And so that is actually done in this little section here, where I is the class number, and we're going to append that to our Y train and our Y test sets, our labels, and then we're going to concatenate the values shown here. So if I just run that quickly, here we go. So we have our X train shape is now in terms of the shape, the size, it's the sum of the two inputs for class 0 and 1 in length, and for the shape, for the X train, it's still 128 samples long, and for the Y, that's the label, that's the actual class representation. It is the same length, but it's just a single dimension, because it's just a, if you like, a column matrix of zeros and ones representing the class 0, class 1. So that's the X train, Y train, and then we've got the same for the X test and the Y test. So now we have the data in a format that we can hopefully pass to Tensorflow, but we'll come on to have a look at that in a minute. So let's just have a look at these frames of data and see what they look like. I'm just choosing a single arbitrary frame, not right at the beginning of each wave file and not at the end because there might be edge effects. So I've just chosen an arbitrary frame index into these arrays of 100, so it's frame index 100. What does the data look like for these two classes? And here we can see the frequency spectra for each of those two classes. So you can now see the features that the classifier is going to look for and be able to differentiate between these two classes of signal. Okay, so we're nearly there. We're nearly ready to build our model. But before we do that, we just need to do a final bit of reshaping of our data sets for Keras. And you can see basically we need to convert our 2D array effectively into a 3D array as shown here. So we have our original length and frame width and an extra third dimension, which is the tensor, which is going to be used by the neural network. So we've converted it from, if you like, a NumPy array into a tensor shape, which we can reuse. It's just a tensor shape though at the moment. Okay, so let's look at our model. Here's our model. We're going to specify the model in these three lines. You can see exactly like the diagram that I showed in the PowerPoint. We've got our input layer with our number of input nodes, 128, there you go. We've got our convolutional layer in the middle with our kernel size, the number of input nodes, and our number of filters. So we're performing 32 filters on each input node. We've got our activation function. We're going to use ReLU. We could use a number of different activation functions here, but in the internal layer, the hidden layer, ReLU is by far the best for this application. We're going to enable biases as well as weights, and so that's our hidden layer. And then finally we've got our output layer, which is a dense layer where basically we get our n classes out. In this case, n equals 2, number of classes equals 2. So the output layer is just going to give us the probabilities that apply for each frame to these, in this case, 2 classes. And for the final stage, we're going to use activation sigmoid activation. On the output layer, we have a few other options. We could use linear, softmax, sigmoid, depending on how we want to treat or handle the probabilities of the results coming out of the hidden layer. And for this, we're just going to use sigmoid, but in deployment where you may be doing some other post-processing of your neural network output, you might want to have a different probability data set results coming out of your neural network. Okay, so that's it. It's very simple. So it's going to be very efficient, very low power, etc. And here we're going to build the model and generate a summary. There we go, nice and quick. So there's our summary in text format and in graphical format if you prefer. If you've not looked at these summaries before, What do they all mean? Well, clearly I'll highlight the text version because it's easy here. We have our three layers, our input layer with no trainable parameters, that it is just the inputs. We have our convolution layer. How many parameters are there? 4,000. This is the most complex layer because it's basically those 128 input samples with our 32-point filters. And then finally we've got our dense output layer going down from 32 to 2. Excuse me a second. That give us our 2 output classes, our probabilities for each of those classes. And basically what we want to do is look at which class has been classified as having the higher probability for the given data that's been applied to the neural network, obviously when we're in deployment mode. One final point about this, what does this none mean? That's a bit weird, isn't it? None, we don't, you know. Well, actually what this means is it unspecified is probably a better way of saying it. In other words, we can apply as many frames to this as we want. So if we have a whole, 100,000 frames of our frequency domain input data, then we can apply all 100,000 frames. If we only had 2 frames, 2 images, whatever, then we could apply 2. So it's basically saying we can apply as much data as we need to the neural network for training, classification, etc., etc. Okay, so that's the network built. Now we need to specify how we're going to train the model. And for that, what we want to do is we want to train the model, but keep the very best model that is generated during that training process. So that's this best model. It's stored as a H5 format. It's a standard format that you can save and load, etc. We're going to compile using the almost ubiquitous Adam optimizer. We're going to test for the sparse categorical cross-entropy loss, and we're going to have our sparse categorical accuracy as a metric for how good the neural network is performing during training, etc. So the accuracy, of course, for this network is key. How good is it at classifying our data? Okay, in terms of our fit function for our neural network, we're going to get the history output of our fit as the data is being fit to the task. We've got our input data, X and Y for training. We've got a batch size, so the data is going to be batched up into batches of 32. We've got our epoch count, which I mentioned before. We've only got 2 classes here, very simple, and we've got actually for this task with just 2 classes, we've got way more than enough data. So 4 epochs is plenty, as you'll see in the graph. We're going to shuffle the data, so we're going to randomize the order of the classes. At the moment, all the data all class 0 is in the first half of the array, of the train array, and the class 1 data is in the second half of the X-train array. We want to shuffle all that around because that obviously makes training better. We've got our callbacks mentioned here. That's our callback here. And here we've got our training to validation split. So what this is going to do is going to split our current 90% of the overall data into a further 80-20 split. So we've got 80% for training and 20% for validation. We've got verbose mode on, and we can fit the network. So here we go. We've got our epochs. Time for me to take a drink of water. There we go. And we can immediately see that the loss is very low, isn't it, already? and even only after like 2 epochs, and accuracy, well, we'll have a look at that in a second, but the loss is very low, so that's good, that's good. The categorical accuracy is the key metric that we are looking at here, and you can see that in terms of the sparse categorical accuracy, we've got an accuracy of 1 straight in. Okay, so that's good, that's good. So we've trained a model, we've saved it. It is now saved as a file on in this case, Google Drive. We can load that if we want into a model. So I'm going to call this my model for time series classification. We're going to evaluate that now with our X test and our Y test sequences that we generated earlier. And here we go with this now completely unseen data, unseen by the neural network. We've got a classification of 99.7%. Pretty good, pretty good. And look at the loss, it's like tiny. Excellent. Okay, but text is all very well, but we like graphs. Let's do a graph. Here we go. Now this is interesting, isn't it? Actually, I think I might have, hold on. My sparse categorical accuracy is showing as 0.5, which is this value here. I should have done this one actually. Okay, so the actual sparse categorical accuracy is showing as 0.5, whatever it was, 0.56. Actually, the most important thing is the validation accuracy. You can see is 1, as good as it may be 0.9999. But you can see, even with this very small network, very small number of epochs, the key thing is the accuracy is pretty close to 1. So that's good. We're good. Okay, so let's generate a confusion matrix to see how that is performing. And again, I've written this code, so regardless of the number of classes, we will generate a larger or smaller confusion matrix. Here it is. So you can see with the test data comparing to the predicted to the true values, we've got a 100% accuracy. So that's good. We could apply some noise to our input. We'd probably see that would there'd be some variation on the results. Actually, just very quickly, what are we doing up here? Let's just take a step back to look at the code for doing this. We're doing the predicting here. This is easy. So we're just passing the code to the model.predict function. So it's predicting the output for our given test input. I've printed the shape here. What's the shape? It's the number of frames in our test data set. It's a 3D tensor so we have basically, as shown here, we have sample steps and features. There are 2 features, class 0, class 1. But actually for plotting the confusion matrix, we actually want to convert that to a 2D tensor where we basically have our input samples and our features. So we are going to squeeze the data. Tensorflow squeeze basically, as you can see here, just removes the one-dimensional axis. And then we are going, actually you can't see that there. I could, here, a bit of code editing for you. There we go. it's squeezed the array, so it's removed that one-dimensional axis out. So now we have our samples and our features. But that's, again, not appropriate for a confusion matrix. Actually, what we want to do is, for the confusion matrix plot, we want to say, well, what is the predicted value, i.e., which of those two has the highest probability, and then we need to compare that, we need to compare that probability to the true label. So we need to convert those two probability values, extract the largest, there we go, the argmax, and then that is the predicted value. And now we can compare the predicted value to the actual value. Okay. Okay, so we've compared the predicted and the true label, and we've got our confusion matrix. Excellent. We've now pretty much done everything we can with the floating point model. Just to wrap up, what we're going to do is to look at the Tensorflow Lite and how we might deploy it on a microcontroller. Now, I'll show you some microcontrollers I've worked with in a bit. I haven't got any connected here because one thing we can do in Tensorflow is we can run a Tensorflow Lite model in a Jupyter Notebook or in Python and see the performance that we will get in the real world. So the first thing we need to do is to convert the model for time series classification to a Tensorflow Lite model. Easy, straight in. I've just used the Tensorflow Lite built-in operations. We then need to generate a quantized Tensorflow Lite model to execute on our, in this case, simulation. I was going to say on our processor. In order to quantize a model, what you need to do is actually provide a representative data set for the quantizer to analyze the data and the model to for scaling. Obviously, you know, if we're in this case we're going to quantize to 8 bits, and so we need to the quantizer, the converter, needs to ensure we're not going to overflow those 8 bits and so on. So that's basically all we're doing here. Again, I've pretty much stuck to the default values, except I'm just quantizing down to 8 bits. And this is going to generate our quantized Tensorflow Lite file. There we go. We can go for a quick run here. There you go. It's given some warnings. You might need to check your statistics, your data values, your scaling. There's lots of things that you might need to check here. And now finally, we have our quantized TensorFlow Lite model that we could load into an interpreter that can run in Python and check the results. So again, we're going to use our X-test as our input data. We're just going to just access the array. We don't know how long it is. You know, if in a real system, we're probably going to process a frame by frame by frame. But in this case, we've just got a data set. How long is it? So we get the shape, we get the length. We're going to extract the min and max values, and we're going to pass the data. We're going to do a reshape. We need to reshape for the interpreter to process the data, as you can see here. And then we're going to pass that to the processor, And here we go, we've got, so I've printed out the min and max. We can see what the scaling is. It can be really useful for, handling out A to D, input, output, all that kind of thing. And finally, I'm printing out the error count, the test accuracy and the test loss of our fixed point model. And fortunately, we're getting the same performance on our fixed point model as we are getting on our floating point model. Excellent, that was quite a long talk. Actually, I don't know how long I've been talking for, but let's quickly flip back to our presentation, our PowerPoint. I'm just going to mention a couple of hardware implementations I've implemented this on. NXP low power LPC 55S69 was actually the very first device I used for this. Was great because it had a DSP processor. And the customer was doing a lot of other DSP stuff and networking and all sorts of stuff. It was an integrated single chip solution, and this just shows you how I'd partition the DSP and the machine learning. This code, I've been talking to some long-time colleagues about the potential for getting this code to run on this M0. We haven't completed that task yet. It's a sort of background fun project time, but we anticipate that even on an M0, this code is going to take around a millisecond for running the DSP and the classification code, so well within real time, and consume around 2 milliwatts of power for performing that classification. So, really ultra low power consumption. Okay, quick summary just to finish off. We've talked about, the benefits of applying the intelligent AI approach of digital signal processing and algorithms to our problem. Reduce cost, power consumption, memory, MIPS, whatever your cost metric is, it helps. We've had a look at DSP and ML basics. Again, this is very basic. There's quite a lot of code here to absorb, but for a real deployable, robust system, there's a lot more code needs to go around this, particularly with the DSP side. And if you want, you can download the code and the WAV files, have a play, and thank you very much. Enjoy the rest of the conference. I'd like to thank Stefan and the team for setting up the conference again, making it all happen. Enjoy the rest of the conference. I'll be here for questions and answers, and please do get in touch if you have any questions. Thank you very much.